Imagine a modern industrial facility operating at full capacity. Human operators cannot manually walk the floor to monitor thousands of distinct physical states simultaneously, every temperature shift, pressure drop, and fluid flow rate across an entire plant. The engineering solution to this scale is SCADA, Supervisory Control and Data Acquisition. SCADA functions as a comprehensive, multi-layered architecture of both hardware and software components. Think of it as the central nervous system of a factory. It translates raw, analog physical reality, like a furnace's heat or a motor's speed, into centralized, real-time digital data. We will deconstruct this architecture from the floor up to the control room. Without this specific architectural framework, safely managing industrial production at modern scale is physically impossible. We will build this architecture from the ground up, using a water treatment plant as our physical model. At the very edge of the process, we have Layer 1, field devices. These act as the sensory organs of the system. These instruments continuously harvest physical process information directly from the environment. They measure exact variables in real time, outputting precise data on metrics like water levels and intake flow rates. But raw sensor data is useless if it has nowhere to go. It requires a localized processing unit to make sense of the inputs. This brings us to Layer 2, the Programmable Logic Controller, or PLC. In remote setups, this may be a Remote Terminal Unit, or RTU. The PLC receives the analog signals from the field devices and executes local control logic. The PLC executes control logic locally, functioning as the primary brain for that specific piece of machinery. At this point, we have local control established at the machine level. However, a series of isolated brains scattered across a facility does not create a coordinated factory-wide system. To monitor an entire plant, we have to solve the problem of connecting hundreds of these isolated PLCs together. That requires Layer 3, the communication network, which forms the neural pathways of our architecture. The engineering bottleneck here is speed and reliability. Data must transfer across this network without packet loss or severe latency. Utilizing standardized, highly reliable industrial protocols like Ethernet, Modbus, or OPC UA is what makes real-time monitoring possible across vast distances. Following this data flow up the chain leads us to its final destination, Layer 4, the SCADA server. This server acts as the central aggregator and database for the entire plant. It collects and stores everything: live process data, alarm histories, event logs, and long-term production trends. We now have the data centralized, but we still lack a way for humans to easily interpret and manage it. That is the role of Layer 5, the Human-Machine Interface, or HMI. The HMI translates the raw numbers stored in the sorter database into a graphical dashboard that operators can read, understand, and interact with. With these 5 tiers constructed, we have a complete architecture that successfully bridges the physical industrial reality with centralized human oversight. To see this architecture in action, let's introduce a physical fault at our water plant. Step 1. A field sensor inside the tank detects that the water level has dropped critically low. Step 2. That analog alert signal is instantly sent to the local PLC. Step 3. The PLC processes this incoming logic, recognizes the fault, and prepares a system-wide alert. Steps 4 and 5. The alert data transmits across the communication network and is permanently logged by the central SCADA server. Step 6. The server immediately pushes this data to the HMI, triggering a flashing alarm on the operator's screen. What's critical to note here is the time scale. This entire 7-step loop, from the physical fault occurring to the physical correction being executed, happens in milliseconds. This architecture enables near-instantaneous physical corrections across an entire facility without requiring manual intervention on the factory floor. While we used a water plant as our model, this exact architectural framework scales to universally support any major industry. Standardizing this framework across a facility reduces downtime, secures operations, and provides the visibility needed for precise energy management. Looking at this Devi automation solutions visual, we see broader applications represented in these icons. SCADA is the prerequisite data foundation. Without it, facilities cannot implement artificial intelligence or the industrial Internet of Things. It is also critical for renewable energy grids and smart agriculture. Because of its universal application, mastering SCADA architecture is the essential first step for any professional seeking a career in industrial automation engineering. Professional providers like Devi Automation Solutions specialize in engineering and implementing these complex systems for factories, facilities, and entrepreneurs. SCADA is the non-negotiable central nervous system of modern industry. Without this architecture securely in place, true automation and the integration of future technologies are simply impossible.